It is a great pleasure to introduce Roser Valenti as a speaker today. Roser, thank you so much to accept the invitation for the Atomic Scale Physics Colloquium today. Let me first give you a brief background of Roser Valenti. So Roser got her PhD at the University of Barcelona in Spain. Then afterwards, she was a Fulbright postdoc at the University of Florida. And afterwards, she started as a DFG Habilitation Fellow at the Universidades Saarlandes and Dortmund, and later on as a DFG Heisenberg Fellow at the Universität Saarlandes. She was later on professor at the University of Frankfurt, and since 2010, she is full professor at the University of Frankfurt. And she has been the director of ITP at the University of Frankfurt and also the vice president of the University of Frankfurt. Roser has gotten many different prizes and recognition throughout the career, but let me just emphasize two of them. So the first one is the Michael Unbizerka-Baum Prize in 2009, and since 2016, she has been fellow of the American Physical Society. From the research point of view, Roser Valenti has worked in many of the most exciting directions in the theory of strongly correlated systems, both focusing on first principles methodologies to understand correlated materials and also on the development and understanding of effective models. Roser has developed both different methodologies for correlated systems, and she has also been working many of the different materials that are correlated and that in particular can be candidates for unconventional superconductivity. And in particular, in the last few years, she has been spearheading some of the most exciting developments on the theory of quantum spin-on liquid candidates and Kitaev materials, bringing theory from first principles and effective models together. And today, Roser is going to tell us about strategies to design quantum materials with exotic properties. So with this, Roser, thank you so much for accepting the invitation. We look forward to your talk, and the floor is yours.
Thank you very much, Jose, for this very nice introduction and for the invitation. It's a pleasure for me to be at this colloquium. I would rather be in Aalto visiting you, but I think we start with the online case. And as Jose said, I'm going to discuss in my talk strategies to design quantum materials with exotic properties starting from first principles. And today I would like to concentrate on two types of systems, those that have an underlying lattice, which is either a honeycomb type lattice or a kagome type lattice. And I will motivate why we are so interested in this type of lattices in the following slides. But first of all, I would like to thank my collaborators in some of the work I will present. So my group in Frankfurt, as well as Steve Winter, who was a postdoc in Frankfurt and moved to Wake Forest. He's there an assistant professor. The group of Johannes Knoller in Munich, as well as Federico Vecca in Trieste. And today I'm going to talk mostly about work I've been doing with Francesco Ferrari, Sananda Biswas, Kira Riedel, and David Kapp. And we're being funded by the German Science Foundation. So since I want to do a microscopic modeling of materials, and in fact, correlated materials, maybe we can set the stage by looking at which are the important interactions that we should take with us in this microscopic description. And I'm doing here a very simplified way of describing the interactions just to then use and see how far we can go in describing the properties of materials, properties such as superconductivity and conventional superconductivity, frustrated magnetism, topological phases. So therefore, which are my four basic interactions that I have here divided into single particle type of interactions versus multi-particle and single orbital versus multi-orbital. And these circles in the middle, basically what they are showing is the strength of interaction. So in a second quantization representation, of course, all electronic systems, and let me first describe the electronic system. I will at some point go into the lattice, but all the electronic systems the electrons have a kinetic energy that we can represent in terms of a hopping matrix element between different sites. This is a single orbital, single particle type of energy scale. Of course, if our electrons are heavy, so they affilling orbitals that are 4d, 5d, or f electrons, the coupling between the spin of the electron and the angular momentum of the electron becomes important. So we are going into this relativistic behavior, and therefore this is an interaction, the spin-orbit coupling, that we should include in our description. Now, of course, the electrons have charge, so there is an important interaction due to the charge of the electrons, which is the Coulomb repulsion. And this is, in fact, a multi-particle single orbital interaction. In the most simplified way, I can represent it in terms of what we call the Hubbard interaction, which is basically we have to pay an energy U to put two electrons on the same side. And if we have a multi-orbital system, there is also an interaction that we should include, which is the Hund's coupling, which is an intra-side inter-orbital interaction. So this is the exchange energy between having the electrons align or anti-align. So now by just looking at these four interactions and its strength, we can start classifying the different materials or material classes that we know as a function of the strength of the interaction. So for instance, if we think about the cuprate superconductors, in these materials, the scales that are important are mostly the kinetic energy and a very strong Coulomb repulsion. In the case of the iron pnictides, these materials are less correlated than the cuprates, but they bring with them a new scale, which is the Hund's coupling, because in these materials, we are talking about multi-orbital, the d orbitals, basically all the d orbitals of iron play a role in the description of the system. If we go now to heavier electrons like 4d or 5d, ruthenides and iridates, then we have all these energy scales at play, and our description has to include them. And as we will see, this is becoming then a rather complex problem, especially because of these multi-particle interactions. And on top of it, we have that these electrons are, and I'm going to describe basically bulk systems or two-dimensional systems, but we are in a lattice, crystalline lattice. So therefore, we also have to include the interactions with the lattice. So having said now these various energy scales, what I want to concentrate today is on the properties of materials that have a layer type of description in the structure, and the layers are either kagome lattices, kagome lattices or honeycomb lattices. And now following these different scales that I introduced, so we can consider the limit of having that the kinetic energy is much larger than the Coulomb and the Hund's coupling with a finite spin-orbit coupling. So we are going to be on the side of itinerant electronic systems. And here, of course, we have a very prominent representative in this range, which is the graphene. But recently, there is now a new class of materials which are based on kagome lattices of vanadium, where they show a very interesting phase diagram. And today I would like to concentrate on, in fact, the nature of the charge density waves in these materials. Of course, we can go now to the opposite limit, so the localized electronic system. So here we will be having metals. Here I'm going to have insulators, because we are going to consider very strong Coulomb repulsion, Hund's coupling, and a finite spin-orbit coupling. And in this case, we are going to talk about frustrated magnetism, either geometrically frustration, like in this kagome lattice, and this is an example of a geometrically frustrated system with spin 1/2 copper coming from the copper atoms that are localized at the sides of this kagome. Or I'm going to then concentrate on what Jose was saying, the Kitaev candidate materials, which have a very interesting frustrated magnetism on a honeycomb lattice with strong spin-orbit coupling, Hund's coupling, and Coulomb repulsion. And if I have time, what I want to do is to take the best of the two walls and start then talking about heterostructures of these materials. So for instance, heterostructure of graphene with alpha ruthenium trichloride, where we have a new playground to find out properties like, for instance, unconventional superconductivity or other type of properties that can come through these heterostructures. How do we treat these materials? How do we treat these basic interactions from first principles? It means that we start with a Schrödinger equation that describes the electronic properties of these systems. However, to solve the Schrödinger equation for a system of interacting electrons is a hard task. And there is, of course, a very, in fact, a theory that has been developed in the last century and has been very successful to describe especially metals, which is density functional, and semiconductors, which is density functional theory. So I'm going to use and extract information of the electronic structure of the materials with density functional theory, and especially in the cases where correlations are important, which is the part that density functional theory is not describing well, because it is there where we are doing the largest approximations. I'm going to combine that with many-body methods. And today I will concentrate on variational Monte Carlo and exact generalization, but one can combine it with, depending on the type of property that you want to describe. So for instance, for correlated metals, then a very good approximation is the dynamic element field theory. There is also another option to, especially if we are interested in predicting materials property, is to forget about, in fact, this ab initio description and just consider statistical methods. And this is also work that we are now doing and trying to develop it further, which is by doing a statistical learning of unbiased data sets and predicting possible topological properties for different type of materials. I don't think I will be able to go to this part, but I can discuss about that if you want. So let me concentrate on this way of describing the microscopics of our systems. And I would like first to go into this range of itinerant electronic systems, where I'm going to concentrate on these kagome lattices. So in this energy range, where we are in fact considering weakly interacting electronic systems, I can start with the case of having in fact just a tight binding Hamiltonian, so no interactions. My electrons are basically described in terms of a kinetic energy with this tight binding energy and this on-site energy. And if by just solving this Hamiltonian, which is easy to solve because this is just a one particle Hamiltonian, if we look now at the corresponding band structure that we get for these two lattices, so starting with the honeycomb lattice, we find that there is a very rich features of the, so this is a two-side per unit cell, so we are going to have two bands, and what we observe is, depending on the filling of our system, we have Banhof singularities that shows in fact this it's a Banhof singularity in the sense that it has this infinite density of states. There are the Dirac points, which is in fact the filling of pristine graphene. And if we now consider the kagome lattice, which has the same Brühling zone as the honeycomb lattice, this is a three-side per unit cell. We are going to have three bands. And on top of these interesting features, as Banhof singularities and Dirac points, we have a flat band. So now, by playing with positioning the filling of our system at these different singularities in this band structure, one can expect to have possible exotic phases, topological phases, and this is what I want to concentrate on in the case now of the kagome lattice. So let me go to this material, which was recently, in fact, synthesized in Santa Barbara by Brendan Ortiz in the group of Stephen Wilson. And this is a very interesting system. So it consists of kagome layers, perfect kagome layers of vanadium that are separated by layers of antimony. And the properties of these systems are the following. So in fact, here, what we have, if we count the electrons, we have 1 electron per 3 vanadium, per 3 vanadiums. The system is metallic. It shows Pauli paramagnetism, so there is no appreciable local magnetic moments. And now what is interesting is that by lowering the temperature, and this happens with all these different cations, the system undergoes a charge density wave transition at about 80 Kelvin. So it means it distorts, forming a charge density wave. And moreover, going down in temperature, these systems become superconductors. And what is now, in fact, there is a lot of work being done for these materials, is a discussion about the nature of this charge density wave transition and transitions, because now a few of them have been observed, as well as the nature of the superconductivity. And I would like to concentrate on the nature of this charge density wave transition. Now, if we look at the band structure, which for these systems is extremely useful, what we see indeed is that we have, of course, we have here these vanadium atoms with 3 orbitals, dxy, dxz, dyz. So what we observe is that the filling of these systems is very near Van Hoff singularities. So in fact, we could think of that the appearance of this charge density wave has something to do with the filling being very near this Van Hoff singularity, which brings a large instability into the system. So the system wants to go away from this unstable behavior. Now, what do we know about experiments about this charge density wave transition? So here I'm showing the STM results by the group of Hassan, where I'm showing at 80K, this is now basically the picture of this charge density wave transition, and we see here the Bragg Q peaks, which form a perfect picture that you expect for this kagome lattice. So now, however, when going down in temperature, the system undergoes this charge density wave transition, and there are these extra peaks coming here to that one can observe that correspond to a 2x2 charge density wave. So there is a doubling of the unit cell. And moreover, what kind of charge density wave has been observed? So the form of this charge density wave, so how the system distorts, it shows like a Star of David or inverse Star of David, so that there will be strong bonds along this hexagon, and then it weaker in the coupling between this triangle. So this is the typical Star of David or inverse Star of David kind of charge density wave. Moreover, this group, what they observe is the following. If you apply a magnetic field in the charge density wave phase, what they observe is that the amplitude of these charge density wave peaks, as being shown here, by changing the direction of the magnetic field, it also changes. And it was interpreted as a breaking of time reversal symmetry on the application of the magnetic field. And this has, in fact, induced a burst of different experiments trying to analyze whether this chiral, so because we are breaking time reversal symmetry, this chiral charge density phase charge density wave phase is being observed in other experiments. So I'm just here listing some articles, but there are many more about this handedness in the charge distribution. However, more recently, by using the same samples, as far as I know, these are the same samples as in the previous work, STM data from Ilya Selikovic, they also go into this phase, into this charge density wave phase, and apply a magnetic field. And here, let me just show you these results here. So this is the amplitude of these charge density wave peaks. We have 3 of them. And by just changing the direction of the magnetic field, basically they don't observe anything special. So in fact, it's very controversial right now whether these charge density waves have chirality or not. So I think this is something that needs to be resolved. So this from the experimental point of view. So let me now go into the theoretical point of view. So we want to understand these charge density waves, and we want to understand its origin, whether we expect to have chiral charge density waves or not. So what happens in these instabilities, in this type of charge density wave instabilities? And now I'm going to start by doing the simplest case. So we are considering that our filling, as in the material, is precisely at the Van Hoff singularity, and because of this Van Hoff singularity, there is a doubling of the unit cell. And let me tell you now what could be the origin of this doubling of the unit cell and of this distortion. So we can consider two scenarios. One is that this is a consequence of electronic repulsion. So we see that we know that exactly at the Van Hoff singularity, we have perfect nesting. So these are the three Q vectors in this kagome lattice, and this is perfect nesting. And therefore, one can expect that Coulomb repulsion, so especially Niers-Neighbor Coulomb repulsion, may be a strong enough interaction to just bring the system out of this instability. And this is, for instance, the proposal by Dena, Titus Neuper, and Ronnie Tamale, where basically they make use of this concept that we have this sublattice interference and perfect nesting, and the electron repulsion will be the one that will bring me into a charge density wave. There is also, of course, another interaction in these materials, which is the electron-phonon interaction, so that the electrons are coupled to the lattice, and there are some phonons. Here, what I'm showing is a phononic type of calculation done by Tan and collaborators, so Bin Hayyan, and this is the group of Bin Hayyan. And basically what they find, so you can do the FT calculations of phonon instabilities, and that the system, due to the phonons that you expect in these materials, will undergo a charge density wave of the kind that it's been observed, so Star of David or inverse Star of Davis, inverse Star of Davis. However, an electron-phonon interaction doesn't have any kind of chirality in it. So we have these two scenarios, and the question is, can we now try to understand which is the scenario that is important for this charge density wave, or it's a combination of both, or it's only one of them? So for that, what we did, we started first with this simpler model where we consider, let's first investigate the effects of electron repulsion. So we have now our Hamiltonian is the kinetic energy, the Coulomb repulsion, and the Niers-Neighbor Coulomb repulsion, and we situate ourselves exactly at the Van Hoff filling. Now, this type of Hamiltonian, so for the moment, I'm not now putting the whole information of the system, only the fact that the filling in these materials is at a Van Hoff singularity of vanadium deep bands. Now, what is known about this model? So, and this is also what exploded this possibility of having chiral charge density waves. So in the 2013, 2012, 2013, there were a few works investigating the phase diagram of this Hamiltonian, and this is by functional randomization groups. So these are, in fact, two groups that investigated what kind of charge density wave phases one can expect in this material as a function of these two interactions, an on-site Coulomb repulsion and a Niers-Neighbor Coulomb repulsion. And if you can see here, I mean, this is now what I call my U as a function of V. So there is, for small values of V, there is what these calculations find is a large region of ferromagnetism, and then some different types of charge-borne orders. So this would be the Star of Davy charge-borne order that we are talking about, and this is the spin-borne order, where we also have a given a spin sign into the bonds. Now, this is a work done also with the same method. However, the phase diagrams don't agree with each other. If you look at them, so here ferromagnetism, in fact, as a function of U, dies out. And then there is a region of antiferromagnetism, which is not here, even though here the values are larger. there is the different phases that appear as a function of B seem not to agree with the phases that we have in this phase diagram. So for us, it was a starting point to say, why don't we first try to understand this phase diagram, and then we will go to the material. So what we did is, let's investigate this phase diagram, but by using a completely different type of approach, where we are sure that we are including the effect of electron correlations and at the various values of U and B. And this is the work of Francesco Ferrari, where what we did, what he did is to do variational wave functions. So which is the idea of variational wave function is basically that you consider an ansatz to describe the correlated nature of your many-body system, of our electronic system. And this wave function is consists on solution, which is the solution of what we call an auxiliary mean-field Hamiltonian that one can express in this form, where the parameters of this Hamiltonian are variational parameters. And in order to include the effect of electronic correlation and even long-range electronic correlations, one includes in the wave function a Jastrow factor, which has this long-range density electronic correlations. And now the idea is to minimize the energy of this wave function as a function of these parameters that come from this auxiliary Hamiltonian and from the Jastrow factor. And with this type of wave functions, one can, in principle, obtain the various phases in the phase diagram of this extended Hubbard model, depending on which are the parameters at which the system minimizes the value. So either you have a charge density wave, charge one order, and you have a lot of variability in getting these phases. So now what is interesting, this is the phase diagram, on-site energy as a function of nearest neighbor, so on-site Coulomb repulsion as a function of nearest neighbor Coulomb repulsion. And what one observes is the following. If we don't have the Jastrow factor, so basically at the mean field level, in this region where the other calculations were getting ferromagnetism, at least in the region of Hughes, ferromagnetism wins if you are at the mean field level. But as soon as you include more correlations, this phase is washed out. And this is, we know that correlations tend to wash out phases that are predicted by, for instance, by Hartree-Fock. So in fact, this is a region of metallic phase. Now, if we go to this region at finite V, this blue region is indeed a 2x2 charge density wave, but the pattern is not the Star of David pattern that one observes in experiments. Moreover, there are other phases of the charge density waves as soon as you go up into this nearest neighbor Coulomb repulsion, which are metallic types. So they are, in fact, they describe different type of dimer states on the honeycomb lattice. So what we are having here is that a phase diagram where there are charge density waves that are induced by electron correlations, but not this type of Star of David or inverse Star of David. Moreover, what we did is try to investigate whether there is some kind of chirality in these different bond orders. But maybe let me show you again this point that I was telling to you, that that introducing more correlations into the system, so more fluctuations, washes out some of the phases that you have at the mean field level. So for instance, if you have at the mean field level, we do have this Star of David. As soon as you introduce the Jastrow-Slater factor, this phase is unfavorable. So you don't get this type of charge order, and the same for the spin bond order. What about the chirality? In the chirality, again, the signs of chirality in such phases, you can investigate them in terms of complex hopping parameters. So if we now investigate how these hopping parameters evolve, the imaginary part of the hoppings goes to 0. So in principle, it seems if you include this description of correlations into this extended Hubbard model, these type of chiral phases seem to be washed out. So what about now the other interaction that we have in this system, which is the electron-phonon coupling? So we can again introduce now the electron-phonon coupling. So here it's introduced in terms of quantum phonons, and this is the corresponding kinetic energy. And we have to, of course, extend the wave function by including not only the electronic part, but also the phononic part. And indeed, by including the phonons, and in fact, this is, we let the distortions of the lattice as the phonons in this material, the kind of distortion that the system favors is a Star of David charge density wave, but of course, without chirality. So I think that from the theoretical point of view, it's rather clear that the electron-phonon coupling is most probably the interaction that is driving the system into this charge density wave. And the question is, in fact, if there is chirality, if there is, in fact, these charge density waves are chiral, where does this chirality come from? So, of course, what I didn't talk about is, and now I'm going to the more realistic description, which is take the whole system. And I'm showing here the band structure of the whole system. So you have vanadium bands, but you have also antimony bands. And the antimony bands, as you can see, they are, in fact, at the Fermi level all over. So antimony is, in fact, the elephant in the room. So antimony is a heavy ion, has a strong spin-orbit coupling. And if one wants a description of these systems, one also has to include these orbitals. But what I wanted to show you here is that the controversy about these chiral, non-chiral charge density waves is not only on the experimental side, but also on the theoretical side. And I think right now one needs to go to these more realistic descriptions. So this was my, let's say, the example I wanted to show to you in the itinerant electronic system. Let me go now, unless there are questions. Shall I stop for questions, or I go now to the quantum spin liquids?
I think that there are no questions in the chat, so you can continue. So
let me continue and go now to the localized electronic system. So now I'm going to consider the fact that I have very strong Coulomb repulsion, strong Hund's coupling, and strong spin orbit coupling. So I'm going to be in insulators, and in fact in mod insulators. And the kind of phases I will be interested in is the so-called quantum spin liquids. Let me first describe what I mean by magnetic frustration. So if we have this type of lattices, like a honeycomb lattice or a triangular lattice, and we have now localized magnetic moments, so let me consider spin 1/2 magnetic moments. If these lattices, the magnetic moments have an antiferromagnetic type of interaction, then it is clear that because of the geometry of the lattice, the third spin cannot be antiferromagnetically aligned to the other two. And this is why we have here geometric frustration. There is another type of frustration that we can induce into our spin systems, which is what we call Hamiltonian engineering, where the idea behind is to construct spin Hamiltonians that only include non-commuting terms, which is also what it's called anisotropic spin interactions. If we have only non-commuting terms, because the spin components of the spin operator don't commute with each other, this is going to induce a lot of quantum fluctuations into your system, and therefore you're not going to expect to have a long-range magnetic order, neither in this type of lattices, nor geometric frustration, nor in this type of Hamiltons engineered in this way. And one prominent example of Hamiltonian engineering is the Kitaev model. So let me just spend 2 slides on why this spin liquid is such an interesting phase. So if we have now geometric frustration, we cannot have a long-range magnetic order, ferromagnetism or antiferromagnetism emerging because the ordering is frustrated. However, the type of state, and this was proposed already in the 70s by Phil Anderson, the type of ground state that one will expect is this spin liquid. So basically, let's consider here, just to make it a little bit representing the wave function on a lattice. So I have here the triangular lattice. And the kind of wave function that one will expect is that the spins will basically form spin singlets and basically linear combinations. So we are having here linear combinations of spin singlets, and then you just fill the lattice with these spin singlets, so that your wave function will be a linear combination of these types of spin singlets covering. And this type of state, in fact, has a long range, but is not a magnetic long range, it's a long range entanglement. It's what it's also called a resonating valence bond state. And this is a state that one is looking forward to find in these geometrically frustrated systems. But even more interesting is not so much maybe the ground state, but it's a type of excitations that you expect in these systems. And the excitations that you expect is what we call fractionalized excitations. So for instance, a spinon, which is a particle that has spin but has no charge. And in general, these are the so-called anion excitations. This is a proposal, in fact, and this is one of the reasons why they are interesting to have materials that have these ground states, these spin liquid ground states, and these fractionalized excitations, following the proposal of Alexei Kitaev, because one can build up with these type of excitations if they are non-abelian. So you can start braiding them and make basically define your cubic in terms of these fractionalized excitations, and you make the operations by braiding them. So this braiding is protected by topology, and therefore you would have a very effective type of quantum computing. So the reality is another one, but this is in fact one of the proposals that is very interesting, and therefore it's important to find materials with this type of states. So what do we know about materials? So if we think about the geometric frustration, we do one of the most studied materials, which is a mott insulator. It's built, this is Herbert method, this is a mineral. It's built of these layers of copper atoms, which have a localized spin 1/2 on a kagome lattice. And for a long time, this system has been proposed that the ground state is a spin liquid. It shows these very diffuse inelastic neutron scattering pictures or patterns. However, these materials are prone of disorder effects, so there is still a lot of discussion about the observation or not of the spin liquid behavior and the corresponding fractionalized excitations in this system. Now, let me go to the Kitaev materials, and I think probably I have now 5 or 8 minutes. Let me go now to the other type of frustrated materials, which is by doing this Hamiltonian engineering. So what are the Kitaev materials? So this, in fact, started by a proposal by Kitaev, and I have to say that the proposal of Kitaev was already, this type of Hamiltonians were already introduced in the 80s by Clement Kugel and Daniel Chomsky. But Kitaev, what he manages to solve this type of Hamiltonians. So what is this Hamiltonian about? So you start with a Hamiltonian on a honeycomb lattice that consists of nearest neighbor Ising interactions, but these nearest neighbor Ising interactions are bond dependent. So if we situate ourselves here in the center of the honeycomb lattice, the Z component of the spin of this site is going to interact with the Z component of the site on the top. Is the X component of this site is going to interact with the X component of this nearby site, and the Y component of this site is going to interact with this Y component. So as you see, this is a highly frustrated model because at each side, we have a different spin component that is interacting with the nearest neighbor. So the merit of Alexei Kitaev was to solve this Hamiltonian which looks rather artificial from construction, to solve it by using the Majorana representation. So basically you substitute the spin operators in terms of Majorana operators. With this substitution, the Hamiltonian is quadratic, so one can solve it exactly. And the ground state is a spin liquid ground state, a Z2 type spin liquid. And the excitations are these fractionalized excitations that I was talking about. So they are gapless Majorana fermions, as well as static gap fluxes. So it's beautiful physics that you have in a Hamiltonian that is exactly solvable. The question was, how do we translate these beautiful properties into materials? And this was done already in 2009 by George Ackley and Guinead Kalyulin, where they basically translated this type of Hamiltonian in this language that we know for spin systems. So in a spin system, you expect to have a Heisenberg interaction, a possible Jałodziński-Moria interaction if the spin orbit coupling is non-zero and you have non-center symmetry, as well as the symmetric term, or also called pseudo-dipolar interaction. This is also proportional to the spin orbit coupling. So this type of interaction can be obtained, it corresponds to this term here in your Hamiltonian, and it can be obtained if you consider, in fact, heavy electrons, for instance, 5 or 6d electrons, in here in a filling of 5 in an octahedral environment that are H-shared. So by considering this type of construction, one can, in fact, get this type of Kitaev interactions. And here are two of the most discussed materials that fulfill these conditions of defining a honeycomb lattice of 4D ruthenium in a filling of 5 electrons, and by having an octahedral environment of chlorine, and by basically doing H sharing. So what we did then is by using first principles calculations and then project it into a spin models, extract the spin interactions in these systems. This is now also another class, which is the iridate. It's the same, also these planar layers of honeycomb lattice. In this case, they are separated by lithium layers. Now, if you basically derive which are the important spin interactions in these systems, indeed the Kitaev interaction is the strongest one. So that's why we call them Kitaev candidates. However, these are not perfect. So let's say you don't have all the perfect conditions that you would need in order to have only Kitaev surviving. You do also get some small Niesnaver-Heisenberg interactions, as well as other off-diagonal anisotropic contributions. And these type of interactions is the one that are responsible for the fact that the ground state of these systems is not a spin liquid, but it's an ordered, long-range ordered magnetic state in a zigzag fashion. Nevertheless, even though the system orders, because it has all these, and this is the values of the interactions that we have for these materials, the orders of magnitude in milli-electron volts, even though it's not a purely Kitaev and it orders, if one looks at the spectrum, here it's in elastic neutron scattering, and the spectrum of excitations is rather anomalous. So this would be what one would identify this at the temperature in the ordered phase of, one would identify this as your Manon excitation to this zigzag order. However, there is all this range of continua, which is being strongly discussed, whether this is still it has something to do with Majorana excitations, or it's basically a decay of magnons. Now, what has been boosting this field even more is this measurement of thermal Hall conductivity. So if you take the Kitaev model and you apply a magnetic field, then the prediction is that the thermal Hall conductivity will be quantized. This is, in principle, what the group of Yuji Matsuda in Tokyo measured for this alpha-ruthenium trichloride. However, these are very controversial measurements, and there is a lot of discussion about whether this quantization has been observed or not, which would tell us that after suppressing the long-range magnetic order with a magnetic field, there would be an intermediate phase of chiral spin liquid. Now, what I want to show you, and I think my time is over, is there is another way.
You can have 5 more minutes. I think that
you give me 5 minutes. Okay,
yes.
Then I will do. I will do the heterostructure. 5 minutes, and I'm done. Now, so this field, so this region here, where we try to get out of the zigzag order by applying a magnetic field, is what I was showing to you with whether there exists an intermediate spin liquid phase or not before going into the field polarized. It's now what is being very much discussed. But there is another way of bringing the system out of this zigzag order, which is by straining the system, because these materials, the coupling to the lattice is very strong. So they have a strong magnetoelastic coupling. So you would expect, if you are able to manipulate the system with the strained fields, you will be modifying these coupling constants and bring the system maybe more to this Kitaev limit. So this is now the idea by creating these heterostructures between alpha-ruthenium trichloride and graphene, especially because this can be done in the lab and has been done in the lab. So what happens when you bring these two systems together? Alpha-ruthenium trichloride is this layered system. It's a van der Waals system. And this is your very nice 2D system. So in principle, it should be easy to form these heterostructures. Now one has to say that there is a big lattice mismatch between these two systems, and one expects effects of strain and doping between the two. So what we did is we did density functional theory calculations where we basically create these heterostructures and look at what happens to the electronic structure. So first of all, what we observe is that there is a strong charge transfer between your graphene layer and your alpha-ruthenium trichloride layer. So you can see it here in the band structure, pristine graphene, you would have the Fermi level here. So graphene gives electrons, so it gets whole dope when you put alpha-ruthenium trichloride on top of it. And here is where you have your Fermi level. And you are going to observe, in fact, some Fermi surfaces coming from this hybridization between the graphene and the ruthenium trichloride. Now, so now what is interesting in the calculations, of course, we tried many cases just to see which is the most stable, is that by doing this heterostructure, alpha-ruthenium trichloride gets strained, because even though there is a big lattice mismatch, it needs to find the most stable configuration. And this type of strain, what it does, it enhances indeed the Kitaev interactions. And there is now a lot of discussion whether you are doping the system because you have these holes from the, so these electrons from the graphene going into the alpha-ruthenium trichloride, whether you could have unconventional superconductivity or Kitaev condo type of interactions. These are the type of devices that have been already done. This is the device in the group of Burkhardt in Stuttgart, where you basically build these bilayers of alpha-ruthenium trichloride and graphene. And since my time is over, I'm just showing now the anomalous quantum oscillation. So indeed, what they observe this is as a function of magnetic field. If you do the fast Fourier transform, basically this is giving you which are these hole pockets that you build into closed hole pockets that you build into the graphene. And the evolution of the temperature evolution of these amplitudes is not following a Lifshitz-Korsavich behavior. And we try to understand that through coupling, through a condo type of coupling between the spins in your alpha-ruthenium trichloride and the conduction electrons, in this case, holes in graphene. And now these concepts are being used in fact, in building ultra-sharp lateral p-n junctions. So there is even some technological application to this type of heterostructures. And with that, I'm coming to the end of my talk. where I basically try to sort of motivate and show how the microscopic understanding of this type of layered systems from the point of view of itinerant electrons or localized electrons has a flurry of phases that are in fact right now very much discussed. Here, for instance, in the case that I showed for the vanadium metallic kagome systems, as well as the Kitaev materials in the case of stronger correlations. And I thank you for your attention.
Thanks a lot, Roser, for this wonderful talk and for telling us about these truly inspiring results on charge density waves in quantum spin liquids. So now we have some time for questions. So if you have any questions, please, you can raise your hand or write them in the chat. Yes, Peter.
Yeah, I was wondering about this these heterostructures. So the last topic. So yes. Of course, on graphene you'll have certain kind of strain, but if you could choose like whatever strain you want, what would be the ideal type? You could think about engineering this.
Yes, very good question. So wait a second. So indeed, here, what we know very well is that the interactions that are harming, let's say, that are bringing us away from the Kitaev are when we have the ruthenium distances too nearby, because this creates what we call direct DD interactions between the rutheniums, and these are harming. These are responsible for all these interactions here. What we want is interactions between the ruthenium that are through the chlorine. That means we need to put the ruthenium atom at a certain distance. So what we want is strain the structure in a way that we blow it up. So that's why pressure is not a good way of basically going into this limit, because pressure basically brings the ruthenium atoms nearby and then you spoil Kitaev. So what you want to do is to blow up the structure, so to basically emulate tensile strain. And this was one possibility with graphene. Now the question is, you can maybe consider other substrates that can make this effect even larger. But this is what we are looking for.
Yeah, thanks.
Yeah, so I have one question that following up this. So in the calculations that you perform, you essentially have one monolayer ruthenium trichlorine on top of a monolayer of graphene. Would there be any advantage in terms of finding a quantum spin liquid of taking a graphene monolayer on the bottom and another one on top? So graphene, ruthenium trichlorine, graphene? Or...
Okay, we have done a few different options. So we also considered what is the effect of two so for instance, you have also this sandwich, so this hexaboronitride. You also play with the sandwich because experimentalists also use a lot this sandwich. Let me see, graphene, ruthenium trichloride, graphene. I think this one we didn't try it. So it may be interesting to look into that. We have tried many cases, but I don't think that we did this one. So okay, maybe good to look into that. Yeah, maybe interesting. Yeah, exactly. Yes, I think we did, because one idea of doing these heterostructures in the community of graphene, where you are more expert than me, the question was whether you can increase the whole doping in graphene in a way, in an homogeneous way, because this is something that has been followed for a long time, by basically doing these constructions and bringing the filling into the Bahnhof. I mean, this has been one of let me see what I have it here. I don't have the Bahn, yeah, the other one. One of the here, whether you can go here, right? So whether you can have some charge transfer that would bring your Fermi level here at this point here. So this has been one of the looking for can I just change the number of carriers by putting something on top of graphene? But this sandwich that you're talking about, yeah, let me have a look into that. I don't think we have done that.
Yeah, all right, thanks a lot.
Thank you.
All right, so I don't see any further questions. So in that case, I will ask one more question that I was wondering. So this one is about the charge density wave in the kagome lattice. So you looked at the phase diagram as a function of U and V, and I was wondering, let's say, how important would it be a second neighbor hopping in the model? So would it leave the phase diagrams more or less invariant, or would it make some change somewhere?
Yeah, that's an important point. You are then, wait a second, let me go into this type of phase diagrams. So what, or in the Hamiltonian, so what you would ask is, what about now going to second neighbors here? So that means that I'm going to consider also this type of interactions, right? So in principle, it's interesting to look into that because you may again increase the phases into your material, into your phase diagram. We haven't done that, but for sure it's an interesting interaction also to fill it in, because we know that in these systems, if you do CRPA and you calculate these values, so basically the way they decrease, even though you have screening, quite a lot of screening because of antimony, but the way they decrease, they are going to be still significant. So indeed, it's an important, interesting suggestion to look into the next neighbors. Why not? Yeah, the next step, okay?
Yeah, of course. Thanks a lot.
Thank you.
All right, so since there are no...
I have a question if it's possible.
Oh, yes, please.
Yeah, sorry, I didn't know where the right hand button is. So, so my question is, like, in this model, you have like a six-fold symmetry, if I'm not mistaken, no, in your charge density wave. Like the inverse standard wave is still six-fold symmetric, but like most of, like there is also like some debate, but there are a lot of people saying that actually the charge density wave breaks the six-fold symmetry because of the, you have like this kind of distortion, but then it's shifted from plane to plane. So I don't know, how does all this like?
Yes, so you're completely right. So here I basically state in the 2D case. So I was now just considering the purely 2D case. However, in the experiment, now, if you think about the third dimension is important, and then the question is how this basically what happens with the charge density wave in the third direction. This we didn't study here. So, but you are right that then you are having in fact your symmetry, depending on how the stacking is going to be broken. Moreover, there is also in some of these systems. There has, I think it was the group of Ilya, that they also observed, I think it's in the cesium system, they also observed an underlying C2 symmetry, so that a breaking already at the level of the 2D. So what I did here was first, what we did is first, let us consider at the simplest level of only one layer, what kind of phases you can expect. Now, to answer your question, we need to do now, in fact, the stapling, or basically these layers, put these layers into the third dimension, and then starting to investigate also the correlation between these charge density waves in between the layers. Yeah, but the experiment is more complex than the model. Yeah, as usual.
All right, good. So if there are no further questions, I would suggest that we can stop the colloquium here. So first of all, thanks so much, Roser, for this wonderful talk and for telling us about these really interesting results. And thank you, everybody, for coming, and see you next time.